Welcome everyone. Under linear time invariant systems, we will look at properties of linear time invariant systems. In particular, we want to relate the impulse response to the properties of these linear time invariant systems. So to recap, in discrete time, the representation takes the form of the convolution sum, while its continuous time counterpart is the convolution integral. So when you take the convolution sum to compute one value of yn, we need to carry out an infinite summation over k, xk, hn minus k. So you can see hn minus k is actually time reversed and shifted version. So we denote that by xn asterisk hn. In continuous time, we have yt equals integral from minus infinity to infinity x tau ht minus tau d tau, which is represented by xt convolved with ht. Characteristics of LTI systems are completely determined by its impulse response, ht in continuous time, hn in discrete time. Okay, first look at the commutative property. If you take the convolution in discrete time, convolution sum, xn convolved with hn is equal to hn convolved with xn. So we know that 4 times 5 is equal to 5 times 4. So this is the commutative property for integers. So it is the same for convolution. Similarly, in continuous time, ht convolved with xt convolved with ht is equal to ht convolved with xt. So here you can see we write hk xn minus k. What this means is x is a signal that is time reversed and shifted when you carry out the summation. So we can verify this for the discrete time. Let's write xn convolved with hn, which is k goes from infinity to infinity, hk hn minus k, xk hn minus k. So we substitute r equals n minus k. So when you consider the limits and the reversing and so on, you can write xn convolved with hn is equal to xn minus r and hr, and these will be switched to get the same representation, which is actually hn convolved with xn. Then the distributive property. Now for integers, this is like 3 plus 5 or something like that, so which is equal to 2 times 3 plus 2 times 5, as you know. So xn convolved with h1n plus h2n is equal to xn convolved with h1n plus xn convolved with h2n, right here. So similar relationship holds for continuous time. So pictorially, in block diagrams, we can represent xt here, and that is fed to h1t and h2t, and this produces y1t and this produces y2t, and those are summed up to find yt. So we can actually write xt gives yt, and this system is h1t plus h2t. So t is missing here. Okay, then the associative property. What this means is if you have 2 times 3 times 5, it does not matter whether you multiply 2 times 3 times 5 or 2 times 3 times 5, it does not matter. So these are, if you just write 2 times 3 times 3, it is not ambiguous how to do that. So xn convolved with hn convolved with h2n is equal to xn convolved with h1n, then convolved with h2n. So a similar relationship holds for continuous time. So as a consequence, we can just remove these parentheses and directly write this convolution. So that's why if you just write it like this, it is unambiguous. There is no confusion about it. Using the commutative property together with the associative property, we can see that the order in which the systems are cascaded does not matter as far as the overall system impulse response is concerned. Okay, so let's look at the associative property using block diagrams. Xn is fed to H1n, and then the output is fed to H2n to get Yn. So we can write this as Hn, which is actually H1n convolved with H2n. So since we can switch these with commutative property, we can write in this fashion. What this means is we feed Xn first to H2n in contrast to this one, and then feed the output with H1n to finally get Yn. So therefore, it is possible for us to switch like that. The order in which the signal is applied to systems does not matter as far as the final output is concerned. Okay, now let's consider about memory, systems with and without memory. A system is memoryless if its output at any time depends only on the value of its input at the same time. The only way that this can be true for discrete time LTI systems is if Hn is 0 for n not equals to 0. So in this case, the impulse response has the form Hn equals k delta n. So where k is actually H0, because you can see all other values of Hn are 0, so the only value that we consider is H0. So the convolution sum reduces to the relation Yn equals k times Xn. So you can see this is, when you see this, you know that the system is memoryless. Why? The output at n only depends on the input at n. If the discrete time LTI system has an impulse response Hn that is not identically 0 for n not equals to 0, then the system has memory. For Ct, for continuous time, the same kind of a relationship holds. So what we need to remember here is, for a memoryless system, Hn must be just some scalar multiple of delta n. Similarly, for the continuous time case. So if you have any other value, then the system will have memory, because it will, in the shifting, when you think about shifting property, it will take values of the input not at n equals 0, but at other places to compute the value. Actually, to properly say it, so to compute the value at Yn, the system will take values other than Xn to compute maybe Xn minus 1 and so on, or maybe x minus plus 1 and so on. Okay, then let's look at the invertibility of LTI systems. An LTI system is invertible only if an inverse system exists that, when connected in series with the original system, produces an output equal to the input of the first system. So what we mean here is that you have xt, and then you feed it to a system ht that produces yt, and then if you connect another system h1t, which is supposedly the inverse of h1t, yeah, you get the same input as the output. So xt here and xt there. So these two things must then be producing the identity system delta t. So let's consider an example. Consider the following relationship of a pure time shift. If the corresponding system is memoryless, what is the inverse system of the system? Okay, so if t is greater than 0, t naught is greater than 0, if the time delay is greater than 0, it is a delay, and it is an advance if t naught is less than 0. Example, if t naught is greater than 0, then the output at time t equals the input at an earlier time t minus t naught. If t naught is 0, the system is the identity system, and that it is memoryless. For any other value of t naught, the system has memory, because it is actually taking input values from future or from the past. Setting input equal to delta t, the impulse response can be obtained like this. So what we do is, instead of x we put delta, then we get the impulse response. So to the system, if you input delta t instead of xt, the output that you get instead of yt is actually ht. Yeah. This is, so therefore if you input t minus, if you convolve xt with delta t minus t naught, the output would be xt minus t naught, just the time delay. That is, the convolution of a signal with a shifted impulse simply shifts the signal. So you can see xt has been shifted to t minus t naught. To recover the input from the output, that means to invert the system, all that is required is to shift the output back. So the inverse system h1t is delta t plus t naught instead of t minus t naught. So therefore, if you convolve ht and h1t, delta t minus t naught convolved with delta t plus t naught, you get delta t. You can try that on your own. Okay, let's take another example. Determine yn and find the inverse system of the following LTI system with impulse response hn equals un. Okay, so let's write the convolution sum expression yn equals xn convolved with hn, which is equal to k goes from minus infinity to infinity hk xk hn minus k. Alright, then we put instead of hn minus k our actual system, which is un, so un minus k. So we know the nature of un, so un is 1 at 0 and for n greater than 0, it is 1, otherwise it is 0. So therefore, as un is 0 for n minus k is less than 0, and 1 for n minus k is greater than 0, by looking at this you can see that, then yn is equal to k goes from minus infinity to n xk. Okay, so this is the summer or the accumulator. As we saw before, the system is invertible and its inverse is this one. So how do you find that inverse? So we can write this as xn, the last value, and the summation up until x k goes from minus infinity to n minus 1 xk. Then we realize that this is equal to actually yn minus 1. So therefore our xn can be found like that. So that is the inverse. So now by putting y equals delta, now in this case you can see this is the inverse system. So the input is yn to that and the output is xn. So instead of yn we put delta. So therefore we must be getting here hn. Actually it is h1n because it is the inverse system. That's the symbol that we use for that. Okay, so we can verify that h1n equals delta n minus 1 indeed is the inverse of hn equals un. So let's do the convolution for that. So un convolved with delta n minus 1. That means un convolved with delta n and un convolved with delta n minus 1. So when you convolve un with delta n, you get the same thing. When you convolve un with delta n minus 1, you get a un shifted to n minus 1. So therefore, if you just sketch it, so this is un, and you can sketch un minus 1, nothing 0 at 0, and all ones. Then if you subtract, you can see you get delta n when you subtract these two. Okay, so we confirm that h1n is actually the inverse of hn. Okay, now let's look at causality of for LTI systems. This is an important concept. What is causality? The output of a causal system depends only on the present and past values of the input to the system. That means the system cannot anticipate future inputs. So that's a causal system and that's a practical system. For discrete time LTI systems, for Yn must not depend on values of xk for k greater than n. So Yn must not depend on values in future. That means values of xk where k is greater than n. So let's see. For this to be true, all the coefficients of hn minus k that multiply values of xk for k greater than n must be 0. Right. This then requires that the impulse response for a causal discrete times LTI system satisfy the condition Hn is 0 for n less than 0. So now if we can take something like that, now let's take Hn equals Un, something like that. U. This is our Hn. So what we do is we have to, this is n, so we in the k-axis we have to write now this is n, right? So I have time reverse that, so I have written h n minus k. Now but right now with this what we are computing is yn, value of y at n. Now, if our Hn minus k has values non-zero after this n, that means the future input values, that means values of xk where k is greater than n, will be considered to compute the current output. So I hope now you understand that. For this to be true, all the coefficients of Hn minus k, that is this, that multiply values of xk for k greater than n. So these are the values k greater than n, right? They all must be 0. So what this means is actually what we have done is taken this and time reversed it and shifted to n, right? So therefore Hn must be 0 for n less than 0. The impulse response of causal LTI systems must be 0 before the impulse occurs. So obviously, so impulse response is the response of the system to an impulse. So impulse occurs at n equals 0. So before that, all must be 0. The impulse response of a causal LTI system must be 0 before the impulse occurs, which is consistent with the intuitive concept of causality. So impulse occurs at n equals 0. So before n equals 0, no output can happen. More generally, causality for a linear system is equivalent to the condition of initial rest. Now this is valid only for a linear system. That is, if the input to a causal system is 0 up to some point in time, then the output must also be 0 up to that time. The equivalence of causality and condition of initial rest applies only to linear systems. So if you take a nonlinear system like Yn equals 3 xn plus 5, so you know that this is nonlinear because of this 5. So this is causal. What that means is Yn depends only on xn or its past values. Actually here it does not depend on past values, only on xn, but the value even before Yn can be equal to 5 because of this constant or the battery voltage. So therefore, although this system is causal, this condition does not apply to that because it is a nonlinear system. So causality of LTI systems for continuous time system is causal if ht is 0 for t less than 0. So your ht must look like something like this or whatever. So it must be 0 here before t equals 0. Causality of an LTI system is equivalent to its impulse response being a causal signal. Yeah. So if you have this system and it's ht, so if you give it delta t, you get ht. So ht must have values, non-zero values, only after the impulse. So impulse occurs here, right? Whatever after that. So it cannot have values before this 0. Okay. So for a causal discrete time LTI system, the condition h equals 0 for n less than 0 implies that the convolution sum becomes, now let's consider this because now h n minus k is 0 beyond n, so therefore you just have to sum until n, up until n, and as yn equals hn convolved with xn, yeah, so we can write that as hk xn minus k. So we know that hk is 0 for k less than 0, so therefore you just had to write k equals 0 instead of infinity. For a causal continuous time system, ht equals 0 for t all t less than 0, so the convolution integral is yt equals minus infinity to t, not infinity, x tau ht minus tau. You can write infinity, but it is not required for you to do that because anyways it will be 0. 0 to infinity x tau x t minus tau. So this is similar to this and this is similar to this. Okay, now let's look at the stability of for LTI systems. A system is stable if every bounded input produces a bounded output. So bounded input means the input does not go to infinity. It is bounded by some value, so it does not go beyond b, or does not go less than minus b. So we can consider as a stable system a pendulum. So if you give it an input shift, it will swing by a finite angle. But if you take the inverted pendulum, for a slight disturbance, it will show a very high response. So this is stable, is unstable. So you can see the brief reasoning what hn must be for a stable system. So we can consider the magnitude of yn. So that is actually, this is the convolution sum, and we get the magnitude of that. So therefore this must be less than that if you take individual magnitudes, and then when you take the magnitude of x n minus k, you know that it must be less than b, so therefore we can take b out. So what that means is absolute sum of hk, this must be less than 0. So you can see if the impulse response is absolutely summable, then yn is bounded in magnitude and hence the system is stable. So for a system to be stable, if it is a discrete time system, the impulse response must be absolutely summable. Absolutely means we take the absolute value here. So similarly, in continuous time, a system is stable if the impulse response is absolutely integrable, as we show here. That means this absolute, you take the absolute value and integrate, the integration must be less than infinity. Okay, we can take examples. Determine whether the following systems are stable. 1. Pure time shift in discrete time. 2. Pure time shift in continuous time. 3. Accumulate in discrete time. 4. Continuous time counterpart of the accumulator. So let's consider first the pure time shift in discrete time. So hn is actually, so pure time shift in discrete time is delta n minus n naught. So we take the absolute value and sum, and it's 1. So it's less than infinity, therefore it is stable. Pure time shift in continuous time. So our ht is equal to delta t minus t naught. So when you put it here, you know that the integral is equal to 1. So therefore it is also stable. Then the accumulator in discrete time, hn equals un for the accumulator. So you try to get the absolute sum of un. It is all ones going up to infinity, so therefore it is actually infinity, so it is not stable, it is unstable. Then Ct counterpart to the accumulator, so the running integral from minus infinity to 2 x tau d tau, the impulse response of the integrator can be found by letting xt equals delta t. So you put delta t here, so therefore ht is equal to ut. So if you try to integrate ut from minus infinity to infinity, you get infinity, so therefore you can see it is also not stable. Okay, now let's slightly change the topics and look at not the impulse response but the unit step response of an LTI system, and then we want to relate the unit step response to the impulse response that we already studied. So there is another signal that is also used in describing the behavior of LTI systems, the unit step response. So the unit step response is very important because it is like having a system and then connecting an input signal to it and turning the switch on, and the input is on after that. So if the input is a battery like of 1 volt and then you turn the switch on, so it is a step input. So therefore it is easy to practically observe this. So you give UN, so step is UN, so you send it to HN, so special symbol, the output is designated as SN. So SN is UN convolved with HN. So you know that by commutative property you can switch these two. So therefore SN can be used as a response to input HN of a discrete time system, LTI system, with the unit impulse response delta n. So we can draw it like that. So UN is the unit impulse response of the accumulator. So therefore Sn must be the running sum of n here, running sum of Hk. Hn can be recovered from Sn using the relation. So we know that the inverse of this is this one. I think you remember that. So because we can write this as Hn plus sum Hk goes from minus infinity to n minus 1, as you have seen many times, and this is actually Sn minus 1. So like this is the inverse of that. So that means if you know the step response, you can compute the impulse response by getting the first difference, or sort of differentiating. So that is the step response of a discrete time LTI system is a running sum of the impulse response. Conversely, the impulse response of a discrete time LTI system is the first difference of its step response. Similarly, in continuous time, the step response of an LTI system with impulse response ht is given by st equals ut convolved with ht, which also equals the response of an integrator with impulse response ut to the input ht. That is, the unit step response of a continuous time LTI system is a running integral of its impulse response. So step response is the running integral of the impulse response. So to compute the impulse response, you would differentiate the step response. This is the step response, this is the impulse response. Alright, let's look at the zero input response. So this is now obvious to us. For a linear system, time linear or not, if we put nothing into it, we get nothing out of it. So if xt is 0 for all t, then yt must be 0 for all t. So if you do not put nothing into a linear system, you get nothing out of it. So similarly, if xn is 0 for all n, then yn must be 0 for all n. So sort of a proof, if the system is linear and xt gives out yn as the output, and if we rescale xt by a, yt must be also rescaled by a. So therefore, if we set a equals 0, then output must be 0. So if you give 0 in, the output must also be 0. So not all systems are like this. Even if a battery is not connected to anything, the output is 1.5. So that is not a linear system. So implications of causality: the system cannot anticipate the input. That is, if let's consider x1t and x2t are equal up until t naught. So if we draw this, so this is, let's say, x1t and x2t, I will draw with a dotted line. They are equal, so I will draw it underneath. After t naught, they can change. After t naught, they can change. So this is x2t and this is x1t. So the corresponding outputs y1t and y2t up until t naught, they also must be equal. Let's say that these are the outputs. They also must be equal. What we are saying is they cannot anticipate that x1t and x2t differed from each other after t naught. So that future event cannot be anticipated. So up until t naught, y1t must also be equal to y2t. Same for discrete time. For linear system, if xt is equal to 0 for t less than t naught, then yt must also be equal to t less than t naught. When you look at this, you can see that. So initial rest, the system does not respond until an input is given. So for a linear system to be causal, it must have the property of initial rest. While for linear system, 0 in means 0 out. So for an LTI system, causality implies and is implied by ht equals 0 for t less than 0, hn is equal to n less than 0. So we will just once again try to justify this. Why does causality imply the above? So the answer is delta t is the input, right? And the output is ht if the system is ht. So delta is 0 for t less than 0, so therefore ht must also be 0 for t less than 0, because the system cannot anticipate. The system responds only after the input occurs, because it is causal, caused by the input causal. So the reverse direction, why does ht equals 0 for t less than 0 imply the system is causal? So we can consider the convolution sum yn xk hn minus k, or similarly the continuous time counterpart also. So yn is k goes from minus infinity to n, xk hn minus k. Only values of xn up to until n are used to compute yn. It's a causal. So similar in CT case. So you cannot use values of xk beyond n to compute the value of n. So therefore this must be 0 after that. So we have seen this before. So we are once again looking at it again. Okay, now let's take the accumulator as an example, and it will summarize also what we learned. The accumulator is an LTI system. So we know that the accumulator is just the running sum. Also we saw that its impulse response is un. Does the accumulator have memory? Is the accumulator causal? Is the accumulator stable in Weibo sense? If invertible, what is the inverse? So we have done this. So hn is not equal to k times delta n, a constant times delta n, so therefore it has memory. Because it actually sums all these things, not delta n minus 1. So un means delta, not only delta n, but all these values are there, right? Is not delta n. So hn is 0 for n less than 0. So this is a causal. See. Is it stable? So if you try to get the absolute sum, it is infinite, not stable. Then the inverse. So we know that the inverse of hn is this. From this we can obtain that. We have seen that before. So let's not worry about it. Okay. So now let's take the inverse of the accumulator. So the inverse of the accumulator. Anyway, let's write it. So xn is equal to yn minus yn minus 1. So therefore the impulse response of the inverse system h1n is equal to delta n minus delta n minus 1. So this is the inverse system. Now, so if you take that one, so we know that un minus 1 is delta n. So we have seen this. So therefore if you give x2n, it is x2 minus x2n minus 1 is y2n. So delta n minus 1 is x1n. So you can see that. Inverse of the accumulator, does it have memory? Yes, because h1n is not only delta n, but it has delta n minus 1 also. So therefore it has memory. Is the system causal? Yes, because h1n has no value less than for n less than 0. So this is this one and this one, right? Minus delta n minus 1. So all these are 0. Then is the system stable in Weibo sense? Yes, we can absolutely sum these two, so it is stable. Okay, so we can take one more example. Under the assumption of initial rest and rest, that is LTI, does it have memory? Is it causal? Is it stable? When we consider this impulse response to this system, you get Hn equals A n un. So we can do a little computation for that. So let's consider, so Hn, by inputting delta n here, we will get Hn here and A times Hn minus 1. Okay, so Hn, so let's compute that. So whenever n is less than 0, delta n is input is 0, so therefore output is 0. So let's put n equals 0. If n equals 0, h 0, h minus 1 is 0 anyways, equals delta 0, that's 1. N equals 1 is h1 minus a times h0 is equal to delta 1 is 0. So therefore h1 is equal to a times 1 is a. N equals 2, h2 minus a, h1 is equal to 0, h1 is equal to a. So therefore h2 is equal to a squared. So you can see you get a squared, a to the power of 3 and so on. So you can write a and un to indicate all values are 0 up until n equals 0. Now does it have memory? Yes, because this is not a scale version of delta n, it's not k delta n. It's not k delta n, so therefore it has memory. Is it causal? Yes, it is causal because Hn is 0 for n less than 0. And is it stable? Yes, if magnitude of A is less than 1. If the magnitude A is greater than 1, then it is not stable. Or similarly, we can do an example for the continuous time system, for a continuous time system, to see whether it has memory, causal or stable. But actually its impulse response are we directly right, so we have to use differential equations to find this, but we will not do it in this lesson. Does it have memory? Yes, it has memory. You can see ht is not actually k times delta t, so you can see it has ut. Is it causal? Yes, because ht is 0 for t less than 0, because it is ut. And is it stable? Yes, because e to the power of minus 2t, you can integrate from 0 to infinity. Okay. So now when we think about these impulses, you can do many things with them. So if you have a system ht, if you give it xt, you get yt. If it is a discrete time system, if you get xn, if the impulse response is hn, you get yn. So if it is the identity system, if you give xt, you get xt. If you give xn, you get xn. Identity means it does not do anything to the input. So therefore ht is delta t, hn is delta n for the identity system. So therefore if you combine two identity systems, you must get the same thing, you must get the same xt here. So what this means is, if you this is delta t and this is also delta t, so that means convolution of two delta t's must be delta t. And there is no problem for discrete time, so when you convolve delta n and delta n, you get delta n. But in continuous time, you have to think about it. For this, you have to use once again the delta t function. So delta t function has height 1 over delta and its width is delta. So therefore, its area is actually equal to 1. In the limit, it goes to delta t. So if you convolve two of these, you get r delta t. So I will not convolve this. You can convolve it on your own and find out that this is starting from 0 going up until 2 delta. You have this. So the question is, when you set the limit to 0, does it give you delta t? Actually it does. So but we need to have operational definitions for some of these things. So if you take d by dt, for example, So operational definition, we use operational definitions through convolution to handle derivatives and integrals of impulse, which are badly behaved functions. This leads to a set of singularity functions. Impulses and steps are examples of these. So if you convolve xt with delta t, you get delta t. So what is d by dt delta t? So you will write it as u1t as the impulse response of that. So if you convolve xt with u1t, you get d by dt xt. So if you have two derivatives like that, then you convolve, you get u2t, u1t convolve with u1t. So these are operational definitions. So with it, if you convolve xt with u2t, you get d squared xt by dt squared. So you can have ukt convolving u1s with the k times with each other. So I think you can figure out this implies that, and u naught t is actually the delta t. So similarly, you can have integrations. U minus 1t is unit step, u minus 2 is a unit ramp, and so on. So you can see you can have integrations going on like that. So you can write u minus m. So u naught t is delta t, u minus 1t is ut, uk times u lt is uk plus lt. So ukt is defined as xt convolving ukt is dk xt by dtk, as you saw before. So in this case, xt convolved u minus mt is the mth running integral. Okay, so that's the end of this lesson. So what we did today was taking ht, the impulse response of continuous time system, and the impulse response of a discrete time system, and relate them to the properties of this system. So we looked at memorylessness, causality, stability, and so on. So for a causal system, you know that ht must be 0 for t less than 0, hn must be 0 for n less than 0 for a causal system. So for a stable system, these two must be absolutely summable or absolutely integrable, depending on continuous time and discrete time. Okay, thank you.